Hello everyone, welcome to lecture 36. So, we have been looking at surfaces, the capillary energy, right. So, capillary energy G of surface is what we have looked at. We defined what is called surface energy, which is capillary energy divided by the unit area, or integral gamma dA will be the total capillary energy, right. So, G capillary. So based on that we have seen that surfaces have internal pressure. I mean, because of surfaces materials develop some internal pressure. We define the equivalence between surface tension and or surface stresses and surface energy based on this idea that at equilibrium the surface energies will develop some sort of surface pressures, internal pressures. Okay. Then we moved on to understanding various things that happen on a surface. A surface itself is not a homogeneous entity. Depending on how you cut the surface, so the surface can have substructures, and these substructures such as terraces, kinks, right. So, they can help us in understanding material growth, right. So, essentially any molecule that just comes onto the surface, first diffuses around and then finds a position for itself, and from that position it will start attaching to other molecules, right. So, that is how growth happens, and the most ideal position for it to find, the most probable position for it to find is what was called a kink position or a half crystal position, and based on the half crystal we have calculated the equilibrium of the gas phase with the solid phase at an atomistic scale, and we said, look, when the pressure, partial pressure in the gas phase of the molecule that is going to be adsorbed onto the surface exceeds that of the partial pressure given by equilibrium condition, then there will be adsorption, otherwise there is going to be desorption, right. So, the molecules just go away, right. So if adsorption dominates over desorption, that is when I can have a growth process that is happening, right. So, it is important for us to understand that this is the substructure of the surface gives rise to these type of growth that happens, and so the substructure comes when you cut the surface, right. So not all surfaces are equally possible, right. So in that context, so it is important to actually understand anisotropy of solid surfaces. Okay. So now, so let us take a Cossel crystal, right. So, this is a solid, and in a Cossel crystal we said gamma 100 is less than gamma 110 is less than gamma 111. By the way, I was just defining, so earlier also I kept on using this word G, right. So, dou G, yeah, so G surface, right. So, this is what is called the G surface is called the capillary energy. Let us just call it capillary free energy. Okay. So, to distinguish it from what is called surface energy. Now, surface energy is so gamma dA integral of this will be G capillary. Okay. So, this will be the definition of capillary energy. Let us keep that in mind. Okay. So that we do not get confused too much. Okay. All right. So, is less than and so on and so forth. Okay. So, now if I plot, right. So, the surface energy, what is called the polar plot of gamma as a function of the angle, it is an angular plot, right. So, polar plot is an angular plot, right. So, I start at the center, I go in the 100 direction, there is some gamma energy associated with it, then I change the angle by 45 degrees, right. So, 45 degrees, that should be the 110 direction, then I change the angle again to 111 direction and so on and so forth. So 100 has minimum energy, right, and then so slight deviation from 100 is going to increase energy. The other smaller energy comes at 110, which is at 45 degrees, then 011 in 2 dimensions, there is no 111, but so if this is 100, this is 10, this is 11, this is 01, right, and that has lower energy again and again, so I have something like this here, and again this has lower energy and so on and so forth, right. So, let me just consider this as the center. Okay, so this is the center. Okay, so and then again I have slightly higher energy, again it goes like this, again like this and like this. Okay. So, roughly this is how the polar plot of surface energy looks like. So, what does it mean? It means actually, okay, so 1 0 or 1 0 0 in 3 dimensions has the least energy, right. So, this is the gamma. I change the angle to 45 degrees, then I get the next least energy. I change the angle to 90 degrees, then these are the same planes that have the same energy, right. But I change the angle by very slight amount, right. So, by 1 degree or something, I am actually increasing the energy by anything, right. So, the slope here is very large, right. So, the surface energy just rises up with a small deviation from 1 0 0. Okay. So, if the deviation is 10 degrees, the surface energy is much more than if the deviation is 45 degrees, right. So, gammas are not monotonically increasing or decreasing with the angle. Okay. And that is what gives all rise to this faceting and other things, as we will see very soon. So, this is so gamma as a function of n, right. So, gamma is a function of n, and gamma is this rugged function, or this so very discontinuous function. It looks like these patterns with spikes, and so these sort of minima points which are very sharp and so on and so forth, right. So, gamma is a very discontinuous function. Okay. So, it is not discontinuous, but so it is not integrable, it is not a very analytical function. Gamma is not an analytical function. Okay. Okay. Now, how does gamma of n for a liquid, and liquid, by liquid I mean an isotropic surface, look like? Isotropic material. Okay. Now, that is just a sphere, right. So, this is gamma, so this is the center, and gamma as a function of n is just a sphere. Okay. Now, you can actually see that the equilibrium shape of a liquid, right, the homogeneous, so equilibrium shape of a liquid was gotten by minimizing, this is reminder to you, minimizing gamma, integral gamma dA, and that gave you a sphere, right. So, there is some correspondence between gamma as a function of n and the shape, this is the shape of the crystal, right. So, there is some correspondence, something to note right now. These two have a correspondence, right. So, gamma and the shape of the liquid have a correspondence. How do they correspond? So the shape, so very simply put, liquid has a radius r, right, and then we know that gamma by r, or 2 gamma by r is the internal pressure, right. So, the correspondence comes from internal pressure. Internal pressure is constant all over, right, and that is what relates the shape of gamma, the polar plot of gamma, and then the polar plot of r, and a polar plot of r is nothing but the shape of the crystal, right. So, the polar plot of r is nothing but the shape of the crystal, and the polar plot of gamma corresponds to polar plot of r through the relation 2 gamma by r, or gamma by r equal to delta p by 2. This is a and delta p by 2 is some kind of a constant, right. So, for a given sphere, delta p is something constant. Okay. All right. So, gamma, so if gamma increases, so to get the same delta p, r should increase. If gamma decreases, to get the same delta p, r should decrease, but the shape is what is important. It is not exactly what is the magnitude of r, but the shape is what is important. Okay. And the shape is a sphere. If gamma is identically uniform at all n, right. So, gamma n is just gamma, then r is a constant and what I get, r of n is a constant and r of n is a constant is a sphere, right. So, that is how you determine the shapes of solids, okay, or shapes of materials based on their gamma plots. Okay. Okay, so gamma for a liquid is a sphere, just to put things in context, but gamma for a solid or an anisotropic material is not a sphere, it is going to look somewhat like this, especially if there are all these crystalline faces. Okay. So, let us keep this in mind, this is gamma of n is a monstrosity like this, right, it is not a simple thing like this. Okay. All right. So, with that, let us do our first problem, which is as follows. So, I want to understand. So, I take an ingot which is growing along 0 0 1 direction, 0 0 1 direction. I make a cut, right. So, about angle theta, right. So, there can be a surface that is formed like this, right, an HKL surface, where HKL are some high indices, right. So, this is 0 0 1 plane or 1 0 0 plane, does not matter, and this is the HKL plane, right. So, which is at some angle theta. Now, I am going to ask, is HKL plane stable or will it split up into two other planes? That is the simple question that I am asking. Just like so I think you know the answer, right. So, if the theta is very small, then it will start splitting up into 1 0 0 0 0 1 and so on and so forth, right. So, it will start forming these terraces, that is what we said, right. So, that fundamentally lets us ask the question, is a plane given any plane, is it a stable plane or is it not stable, and does it just perturb, does it just spontaneously decompose into a set of other facets, right. So, is a given plane stable or does it decompose into a set of other stable facets. Okay. So, given plane or facet, let us just call it a facet, okay. Surface, the plane that ends a surface is called a facet, okay, in a crystal. Okay. All right. So, that is the question we are asking. So, essentially so the question so just to put that very simply in terms of mathematical terms is, I have a plane like this and I am asking the question, is this plane going to just be like that or will it sort of decompose, or so when will this plane decompose into a set of these two other planes, right. So, how do I draw it? Okay, 1 second. Right, so okay, something like that. Okay. So, this is a plane, I am going to call it, this plane has an area of A3, okay, and it is a normal vector, that plane is in blue. So, I am just going to write it in blue. That plane has an area A3, sorry, A3 and normal vector N3, right. So, that is the blue plane, and the red planes have area A1 with normal vector N1 and A2 with normal vector N2. Now, I am asking you the question, it is a very much more simpler question than is this plane stable overall. I am just asking you, under what conditions, if these are the only options available for me, right, under what conditions can the plane A3 N3 split into A2 N2 and A1 N1. Okay. So, that is the simple question that I am asking. I mean, that is even simpler than this question, right. So, so I am actually going to calculate the total surface energy of A1 plane and A2 plane, and then compare it with the surface energy of the A3 plane and see if it is less or more, right. So, total capillary energy, not the surface energy. Okay. So, that is the idea. So, if the surface energy of two planes put together is less than the capillary energy of the A3 plane, then A3 plane is unstable. It will of course split into A1 and A2. Okay. Okay. Fine. So, we have some geometric, let us solve this problem. We have some geometric relations. So, one is A3 N3 just vectorially adds up to give A1 N1 plus A2 N2. Okay. All right. So, that is the first relationship. Then, so, so gamma 1 A1 plus gamma 2 A2 is the total surface energy, total capillary energy of A1 plus A2 surfaces, facets. Okay. So, I am going to call gamma 1 A1 plus gamma 2 A2 as some gamma 3 star, right, and A3, right. So, this is something that I have defined. I define a gamma 3 star, right, such that equation 1 is valid. Okay. 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 So, this is or equation 2 is valid, right. So, this is equation 2. Okay. So, then I am going to take 1 and I am going to decompose, I mean I am going to do some algebra now, right. Let us do it in some other color. So, equation 1 I am going to write it as A3 gamma 3 inverse, right. So, essentially gamma 3 inverse is 1. Okay. So, there is a method to this madness, just bear with me, and at the end you will understand, so the beautiful geometric constructions and other things that come out of this, right. So, looking at the polar plot, we should be able to say if some orientation gamma of n is stable or unstable, right. That is what we are doing. Okay. N1, okay, sorry, N3 is equal to A1 gamma 1 inverse N1 plus A2 gamma 1 gamma 2 inverse N2. Okay. So, this is I did nothing, essentially I inserted 1 written as gamma 3 inverse, or gamma 2 inverse, or gamma 1 inverse. Okay. So, 1 is written like this. Yeah. So, now I have I can rearrange things a bit, that implies A1 gamma 1, okay, times gamma 1 inverse N1 minus gamma 3 I will just write gamma 3 star for a reason. Okay. So, gamma 3 star inverse N3 plus A2 gamma 2, right. So, I am just taking A3. So, essentially I am writing, okay, let me add one more step and then it becomes more easier for you to understand. So, I am writing A3 gamma 3 star now as A1 gamma 1 plus A2 gamma 2, that is the definition of A3 gamma 3 star, right. So, once I write that, so then this equation can be rewritten as A1 gamma 1, right. So, A3 gamma 3 is A1 gamma 1, there is an A1 gamma 1 here, plus A2 gamma 2. Okay. A1 gamma 1 times gamma 1 inverse N1 minus gamma 3 star inverse N3, okay, is equal to A2 gamma 2, right. So, gamma 3 star inverse N3 minus gamma 2 inverse N2. Okay. Or in other words, if I have to calculate what is gamma 3 star inverse N3, that is equal to 1 by A2 gamma 2 plus A1 gamma 1, okay, times A2 gamma 2, okay. So, sorry. A2 gamma 2 times gamma 2 inverse N2, okay, that is a vector, plus A1 gamma 1 times gamma 1 inverse N1, okay, that is another vector. Okay. So, it looks like it is okay. So, now I am just going to plot the inverse of gamma, polar plot of inverse of gamma, that is gamma inverse, right. Now, if gamma 2 inverse is here, gamma 1 inverse is here, okay, in the polar plot space, then this equation actually suggests to me, this is equation 3, right, that gamma 3 inverse should be on this line here, right. So, and then so it is divided in the ratio of their areas, right. So, A2 gamma 2 A1 gamma 1. So, but this should be here gamma 3 inverse, gamma 3 star inverse, and should be on this line. Okay. So, this is what this is saying, it does not need to be perpendicular, it can be anywhere, and the weight exactly is determined by A2 gamma 2 and A1 gamma 1, right, or in the N3 direction, essentially in the N3 direction it should be there. Okay. So, this is N1, this is N2, gamma 3 N3 should be on the line connecting this gamma 1 inverse and gamma 2 inverse. Okay. So, let us redraw that, the simplest thing, again I will redraw that in red. So, this is the gamma inverse of N plot. Okay. So, gamma 1 inverse, this is in the direction N1, that I know, this is gamma 2 inverse in the direction N2, right. Then I draw a line connecting these two, and on the line connecting these two, so N3 is in this direction, let us say, gamma 3 star, the way I have defined it, should be here. Okay. Okay. Now, but the plane of interest to me has a surface energy of gamma 3. Okay. So, A3, which is the plane of interest to me, has a surface energy of gamma 3. Now, when gamma 3 is greater than gamma 3 inverse, okay, then A3 is unstable, gamma 3 star, right. So, gamma 3 star is arising as some kind of a mean between gamma 2 and 2 and gamma 1 and 1, right. So, the condition is when gamma 3 is greater than gamma 3 star, A3 is unstable, or in other words, when gamma 3 star inverse is greater than gamma 3, then A3 is unstable. Okay. Or A3 is stable when gamma 3 is greater than gamma 3 inverse, sorry, I have to go from, this is the direct space, this is the inverse space, inverse gamma space. Okay. So, gamma 3 inverse, gamma 3 star inverse, then A3 is stable. Okay. So, now in this plot, right. So, if the gamma 3, right, so I have a triangular plot with gamma 3 star inverse, which is here. Okay. Now, if, and that has to be along N3, right. Now, if gamma 3 is here, let us say gamma 3 star, this is, if gamma 3 inverse is here, that means gamma 3 inverse is less than gamma 3 star inverse. Okay. And if that is the case, gamma 3 star, gamma 3 inverse is less than gamma 3 star inverse, those planes or those facets are unstable. Okay. So, if it is inside this line, it is unstable. If it is outside this line, however, if the gamma 3 inverse is here, right. So, if the gamma 3 inverse is outside the line, outside the triangle, then those facets are stable. Right. So, if gamma 3 inverse again I have to keep, yeah, so gamma 3 inverse is less than gamma 3 star inverse, which means the gamma 3 inverse is lying inside this triangle, right. So, on this normal it lies inside this triangle, then these planes are unstable, right. But by the way, gamma 3 and gamma 3 star is a plane that I have defined, right, as having a total energy of gamma 1 A1 plus gamma 2 A2, but having a normal vector which is in this which is the same as the normal vector of the A3 plane, right. So, that is how I have defined it. So, all gamma 3 and gamma 3 star comparisons happen along just this line, okay. So, they just happen along this line, right. So, nothing else, right. So, that line is defined by N3. Okay. Now, on this line N3, if gamma 3 star lies inside this triangle, then that gamma 3 star is unstable. If gamma 3 inverse lies outside this triangle, then that gamma 3 then that A3 is a stable plane. Okay. Now, what does it mean that A3 is unstable? It just means that A3 can split here into A1 and A2 splits, right. So, there is a spontaneous decomposition of A3 into A1 and A2 because the surface energies want it to split. Okay. So, then I will have faceting, or so the terraces can be explained like that, right. So, especially if there is a split. Okay. So, this is the problem that we have solved. I am asking you the question, when is this plane going to split into this plane and this plane? That is the simple question that I have asked, okay. Or is this plane just going to be stable by itself, right. So, if this plane becomes unstable, then it splits into this and this, and that criterion now we have gotten by looking at the gamma, alright. So, this is gamma as a function of n, right. So, gamma as a function of n, this has the least energy, this has again least energy, this has again least energy, but then the energies start increasing, right. So, this is still this is still a surface which does not have cusps like I was showing you, right, but so you can assume that these are so they have smoothened it out a bit, right. So, this is more close to isotropic surface, but there is anisotropy. Okay. So, now in such a surface, what I am going to do is I am going to plot the gamma inverse 1 by gamma. Okay. Now, 1 by gamma has maximum the minimum of gamma is here. So, the maximum of gamma inverse will be here, right. Similarly, there is another maximum here, there is another maximum here, there is another maximum here, these are maximum of gamma inverse. Okay. Now, I am asking you the question that so given any point, right. So, given so given this point here, right. So, I am asking you the question, will this surface, is this surface stable against a perturbation, or is it going to split up into other surfaces, right. So, I ask you the question, is it going to split up into this surface and this surface, right. So, what am I going to do? I am going to look at gamma inverse plot, and then I am going to draw a line between these two surfaces, and I am going to say that this point is actually inside this line. So, of course, this can split up into this surface and this surface. Then I ask the same question about this surface. Will this surface split up into some surface here and some surface here, and the answer is yes, because this point is also in between that line, inside of that triangle. Okay. So, let us show it more carefully. Okay. So, in the text here, right. So, I have this was the gamma plot. Okay. Okay, I am very bad at drawing, but so you get the gist, right. So, this is gamma as a function of n. Okay. So, then correspondingly, if I draw gamma inverse as a function of n, right. So, that is going to have a cusp here, okay, that is going to have a cusp here, that is going to have a cusp here, and that is going to have a cusp here, right. Again, I ideally want to make all these cusps symmetric about the center, but maybe if I keep teaching this class 20 times, then probably 21st time I will be able to draw it better. Okay, anyway, so this is the surface energy. This is gamma inverse as a function of n. Okay. Then I ask you a question. I take a point here, and I ask you whether this gamma inverse of n in this case, right. So, but it is the same point here, right. So, it is the same point which is at the same n, right. So, and that n is here somewhere, right. So, this is gamma of n. Is this a stable point? Is this a stable facet or an unstable facet, right. Now, what should I do? Unstable against what, right. So, you tell me how, what should it split into? I am going to say it, let us say it splits into this plane and this plane, right. Okay. So, then let me actually do this construction, and I see that this point is inside this triangle, right. And so the gamma 3 star inverse is here, gamma 3 inverse is here, and as a result actually gamma gamma 3 will split up into A1 and A2, right. Okay. Then I ask you the same question about A1. Okay. So, is A1 stable against perturbation, right, and perturbation to what? So, let us say let us talk about 2 points here and here, and in fact when I draw a line there, A1 looks to be so inside that line, right. So, A1 will also split up into this point and this point, right. So, like that what I can do is I can start drawing these tangents, which are just straight lines that are going to encompass these points, right. So, between these two tangents I have a stable surface, sorry, I have unstable surfaces, right, and otherwise these are all stable surfaces, because if I take 2 points here, right. So, and then I draw a line here, right. So, this gamma 3 star is actually inside, or gamma 3 is outside. So, this is a stable surface, right. This is a stable surface. I have so I just follow this trajectory of stability, and trajectory of stability is going to be this pink trajectory. Okay. So, wherever these tangents start splitting up, that is where the stability. So, okay, so wherever these pink surfaces are, that is the trajectory of stability. Okay. So, if there is a point here, right, that point is going to split up into this facet which is A, and this facet which is B, and this point is C, right. Similarly, if there is a point here, that is going to split up into this facet and this facet, right. So, this is like my coexistence, right. So, even in phase diagrams I have a coexistence of this facet and this facet, right. So, this is let us say D splits up into E and F. Okay. Similarly, something like D, E, F, G splits up into H and I. Okay. But whereas if I have J here, J is a stable surface. Okay. So, these lines actually that are outside this define the coexistence, right, that are outside this plot defines the coexistence of this plane and this plane in different areal fractions, right. So, but so essentially if there is a plane here, that will eventually split up into E and F, that is the global stability. Okay. Okay. Now, so then I am asking you the question, so in the context of terraces, right. So, for terraces, so let us say the 0 0 1 planes are, or so 0 0 1 planes have a huge cusp, right, and so do the 1 0 0 planes, right, and then I go to a small miscut which is here. So, this is the point that I want to see. Okay. So, then if I actually this is gamma as a function of n, then if I plot gamma inverse as a function of n, right. So, this huge cusp here becomes a huge spike, and here also it becomes a huge spike like this, right. And now I am going to say that look, I am actually looking at some surface which is at a small deviation, and that small deviation is here, right. And because of the spiky nature, right. So, when I do this nice line like construction, so the only point that becomes stable is actually this 1 0 0 point, right. So, there is no region of stability. Earlier, because of some kind of a smooth nature of this surface, there is some region of stability, right. So any surface here will be stable, right. But typically in crystals these are all huge spikes, and if these are all huge spikes, you know, so only if I am at that 1 0 0 point or 0 0 1 point am I stable, right? Otherwise I am going to split. I am going to split into you know, whatever is given by this dotted line. Okay. So, typically, you know, okay. So, always I am going to split into a 0 0 1 plane and a 1 0 0 plane. Okay. So, you know, so if I have a small miscut, that is what this is saying. If I have a small miscut of, let us say, less than 1 degree, less than 0.5 degree or something like that, right, yields terraces. And again this is in a causal crystal, okay, of orientation 0 0 1 and 1 0 0. Okay. Now, of course, you know, so depending on if I am closer to 0 0 1, that means I have more percentage of 0 0 1, right. So the terrace will be more like this, and then less percentage of 1 0 0 is less in you know, fraction, and 0 0 1 is more in fraction, and this is exactly similar to your lever rule that you use in phase diagrams, right. So this is similar to lever rule. So if my point is closer to this quote unquote phase, then I have more of this phase and less of this phase. But if the point is closer to this phase rather than that phase, I have more of these faces. In this case, these are facets. Okay. So there is a very close resemblance of this surface energy constructions based on the gamma plot with you know, your phase diagrams, right. So your lever rules and things like that. Okay. So that's this is well known. Okay. All right. So that's how you get the terracing, right. So a small miscut is going to give you terraces, okay, and terraces and the substructures of surfaces that we have seen, kinks and you know, and so on and so forth. Okay. So with that, let's take a pause here. Let us stop this class here, and you know, so the idea is, you know, so when do surfaces generally split? So I can look at, you know, so now I do not have to do this calculation of surface by surface. Okay, will this surface, will the 31 22 36 HKL split into 21 21 20 and you know, something else, or can I give a global stability diagram? I can actually give a global stability diagram by looking at the gamma inverse plots, and the gamma inverse typically tends to be these cusps, and so the global stability, you know, so except at the point of the cusp, which is a singular point, right, the stability is not there. Even if I am slightly mistilted by 0.1 degree or something, I will still find, you know, so I am away from the cusp, so I will still be in this region of coexistence of two different phases, and these two different phases are 0 0 1 and 1 0 0, right. Now the percentages depend on what is the miscut angle, right. So if the miscut is large, then the percentage of you getting the 1 0 0 facets are also large. If the miscut is small, and of course that means more terraces, right. But if the percentages are small, you know, so if the miscut angles are small, the percentage of you, the terraces, right. So the terrace structure, or you getting this 1 0 0 faces also reduces. Okay. So it's a very simple calculation in that fashion. Okay. So with that, let's take a pause here, and then I'll again see you in the next class. Thank you very much.